Okay, welcome to video 8.3.3, the last in the 8.3 lesson. So today we're going to be talking about successive ionization energies. So when we talked about ionization energy, we talked about that being the energy required to remove an electron and just one electron. So a successive ionization energy then is when we're going to remove one electron after another, after another, after another. And then we're going to see that that energy is going to increase for each electron that we remove. It's going to require more and more and more and more electron or energy to remove them. Okay, so for this one, we're going to look at boron. So boron is number 5 on the periodic table. It has 5 electrons. So we are going to draw the orbital diagram for boron and then write the equations for all of the successive ionization energies for them. So for the orbital diagram, it's got a 1s orbital. So there's my 1s orbital. It has a 2s orbital, it's higher energy. It also has a 2p orbital, which is a little bit higher in energy as well, but still on level 2. Okay, so we have, let's see here actually, let's go ahead and fill this. We have 5 electrons, so 1, 2, 3, 4, 5. And I'm going to go ahead and number these in the order they're going to come off. So the first one to come off will be on the outside. We're going to move from the valence in. So this is the first electron that will be coming off. This is the second one, the third one, the fourth, and the fifth. And since these 2 electrons are degenerate, that means they have the same energy, remember. It doesn't matter if you have 4 and 5 flipped here or 2 and 3. It's the same thing. Those electrons have the same energy. All right, let's go ahead and now look at their equations. So for the ionization energy of boron, the first ionization energy is 800 kilojoules per mole. That means it's going to take 800 kilojoules to remove 1 mole of these electrons, of number 1 electron, from 1 mole of boron atoms. So to do that, I have boron plus the energy involved. So we have to put the energy in to take an electron off. So plus 800 kilojoules. And that's going to yield boron plus the electron we tore off. Okay, that's the first equation. The second equation is going to start with B+. So that boron ion plus the ionization energy it takes to take off the next electron. So that's going to be 2,430 kilojoules. That's going to yield B2+ plus the next electron. So go ahead and pause the video, follow that trend, and see if you could figure out the rest. All right, welcome back. So we're going to start now with B2+. And so we would be in this state where we take off this electron and this one, right? So we'd only have 3 left here. Plus the energy it's going to take, 3659 kilojoules. It's going to yield B3+ plus another electron. And so now we've removed 1, 2, 3 electrons, and we only have those 2 left on the bottom. So B3+ plus 25,000, 20 kilojoules. It's going to take a ton of energy to do this. B4+ plus an electron, and now we only have 1 electron hanging out left. So B4+ plus 32,810 kilojoules yields B5+ plus an electron. Okay, those are all the equations for the successive ionization energies. Now we're going to spend the rest of the time explaining the ionization energies. So for part A, ionization energy 2 is about 3 times greater than ionization energy 1. So if we look at ionization energy 2, it costs about 3 times as much energy to remove this electron than it does that electron. Well, why? Well, it turns out that ionization energy 2 removes an electron from the 2s, while ionization energy 1 removes the electron from the 2p. Because the electron on the 2s is in a lower subshell, it's more attracted to the nucleus. That's going to require more energy to remove. So, ionization energy 2 removes an electron from the 2s, while ionization energy 1 removes an electron from the 2p, which is a lower shell. Because The electron in 2s is in a lower subshell. It is more attracted to the nucleus, so it requires more energy to remove. Okay, so why is ionization energy 3 greater than ionization energy 2? So ionization energy 3, why does that cost more energy than ionization energy 2? Well, for ionization energy 2, to remove this electron, because the removed electron is paired in the 2s here, there's already a greater electron-electron repulsion. So these are already repelling each other, and 2 kind of already wants to leave because there's repulsion there. So it's going to require less energy to remove this one when it's paired than the one from the half-filled 2s, because now there's no repulsion there, so it's okay hanging out there. So both ionization energy 2 and ionization energy 3 remove electrons from 2s. For ionization energy 2, because the removed electron is paired in 2s, there's already a greater electron repulsion. So it requires less energy to remove than one electron from the half-filled 2s. In ionization energy 3's case. Okay, so now let's compare the next two. Ionization energy 4 is about 7 times greater than ionization energy 3. So 4 is about 7 times greater than 3, so that's a huge jump. So when you start to take this electron, number 4, out of the 1s, that costs a whole lot more energy than taking this last electron from the 2s over there, even though these guys are paired. So why do you think that is? Well, in ionization energy 4, the electron from the 1s, let's go back up here, from the 1s is now going to be removed. While in ionization energy 3, the electron from 2s is removed. So electrons that are in these lower shells, they're way more attracted to the nucleus. This one's right next to it. So it's going to require even more energy to remove. Even though these electrons are paired, it can't overcome that energy that's required. So in ionization energy 4, the electron is removed, while in ionization energy 3, the electron from 2s is removed. Electrons from lower shells are more attracted to the nucleus. So they require more energy to remove. Okay, so last question. Which ion is boron likely to form? Explain. So remember, maximizing unpaired electrons minimizes repulsion between the electrons, and it increases stability, as does a full valence shell. So which ions do you think, or ion, will boron form? So please pause the video, think about that, and then come back. Okay, so it turns out that boron is very likely to form a 3+ ion, so B3+. And that's because it has 3 valence electrons. And so those are the electrons in its valence shell, and they require less energy to remove. So if we look here at the ionization energies themselves, we have 800, 2400, 3600. Those are all pretty close to each other in the scheme of things. And then we look up here. Look how much energy it's going to require to take off any more electrons. 25,000, 32,000. So there's a big jump from there to there. We're not likely to make that jump, but we're pretty likely to be able to get these smaller amounts of energies in. So B3+, because those are the electrons in the valence shell, and they require less energy to remove. Okay, so we have gone over quite a few topics in lesson 8.3. So because of that, you have a nice summary of all the periodic trends on your last page here. So all of these summaries are going to give you the evidence and just kind of sum up all of the trends. Now, it's important that when you're being asked to, justify an answer or explain, you wouldn't just list, the trend. So you wouldn't say something like, if you go down to family, the ionization energy decreases, or whatever. You would say, okay, the ionization energy decreases because of, and then bring up all your different evidence for that particular example. Don't just list the trend, because that won't earn you credit. You have to explain the trend as well. But here is a nice summary for you to be able to remember all of the different trends. Okay, so that is it for lesson 8.3, and I'll see you next time for Unit 9.